Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today we're taking a deep dive into the engineering solutions developed really since the Industrial Revolution. We're tackling a huge problem. How do we manage and control stationary source pollution, the stuff hitting our air and water?
Yeah, and it's not just history, right? It's a constant engineering challenge today. We're looking at big industrial activities, think power plants, metal processing, manufacturing. These are major stationary sources, pumping out pollutants continuously. The scale is just massive.
And the engineering challenge that comes with it.
Exactly.
Colossal.
What's really interesting is how much the law drives innovation here. You've got the EPA, the Clean Water Act, RCRA. These aren't suggestions.
Oh, definitely not. They set hard limits. They force engineers to get creative, turning simple disposal into really complex chemistry and flow control systems.
So the regulations set the bar, and engineers figure out how to clear it efficiently and hopefully cost-effectively.
That's the name of the game. Performance first, then optimize the cost. Okay, let's kick things off with air pollution. The big challenge there is managing the 6 criteria pollutants. These are the ones defined by health standards, the culprits behind smog and acid rain. We're talking carbon monoxide, CO, nitrogen dioxide, NO2, ozone, particulate matter, specifically PM10, so less than 10 micrometers, sulfur dioxide, SO2, and lead, PB.
Right. And for stationary sources, controlling these usually falls into 3 main buckets, 3 engineering philosophies, if you will. First up is pre-process control. Basically, clean the fuel before you burn it. Think coal cleaning, removing sulfur or ash beforehand.
Makes sense. Get rid of the problem before it starts.
Then you have process modification. This is about changing the actual combustion itself or maybe the manufacturing process to stop the pollutant from even forming.
Like the low-NOx burners we hear about.
Exactly like low-NOx burners. That's a prime example. Change the flame to prevent NOx. And the third way, that's the classic post-process control, sometimes called end of pipe. Here, the pollutant is already formed and you clean it up from the exhaust gas after combustion. Flue gas desulfurization systems, the scrubbers, fit right in here.
Got it. Let's dive into the first big one then. Sulfur dioxide, SO2. This is mostly a fuel-borne pollutant, you said.
That's right. The sulfur is chemically part of the fuel, like coal or heavy oil, before it even gets near the furnace.
So the pre-process option seems obvious. Switch fuels, maybe.
Yep, fuel switching is one way. Go from high sulfur coal, like you find in the eastern U.S., to lower sulfur western coal. Or try cleaning the coal you have, but there's a catch, a big one.
Okay.
Even with the best coal cleaning tech, for those common high sulfur eastern coals, you typically can't get more than about 30% of the sulfur out. Not without spending a fortune anyway.
Wow, only 30%. So like 70% or more is still going into the furnace?
Pretty much. Which means the main fight against SO2 often moves downstream to post-process control. We're talking flue gas desulfurization, FGDs, scrubbers.
Right, scrubbers. And there's a choice there between wet and dry systems.
Correct. Wet scrubbers are generally the high-efficiency champs. They can consistently pull out 90% or more of the SO2. They usually use a slurry of lime, that's CaO, or limestone, KCO3. This slurry reacts chemically with the SO2 gas.
To form what exactly?
It forms calcium sulfite, KSO3, or calcium sulfate, KSO4. Gypsum, basically, if it fully oxidizes.
Ah, but I remember hearing those reaction products can be tricky. They cause problems, right?
Oh, they absolutely can.
Yeah.
Calcium sulfite and sulfate aren't very soluble in water. So the big operational challenge is managing this slurry that forms and, crucially, preventing scale deposition.
Scale. Like lime scale in a kettle.
Sort of, but on an industrial scale. It's this sticky, solid material that builds up inside the pipes, the reactors. It can choke the whole system if you don't manage it constantly. It's a maintenance nightmare.
Okay, so that's wet scrubbers. What's the deal with the alternative, the dry scrubbers or spray dryer absorbers?
Dry scrubbers, or SDAs, they trade some of that top-end efficiency for lower costs, both capital to build them and operating costs. Plus, they produce a dry powder waste, which is much easier to handle than a wet slurry.
And the efficiency?
Typically lower, yeah. Maybe in the range of 70 to 90% SO2 removal.
Okay, now you mentioned a counterintuitive insight about cost.
Ah, yes. This really gets to the heart of engineering trade-offs. When you look beyond the sticker price, the installation cost, and instead measure the true performance metric, the cost per ton of SO2 removed, something interesting happens.
What's up?
The cost often becomes surprisingly comparable across different technologies, even between the high-efficiency wet scrubbers and some lower-efficiency options.
Wait, hold on. If the cost per ton removed is similar, why would anyone choose a technology like, say, furnace sorbent injection, which might only give you 50 or 70% reduction? Why not always go for the 90+%?
That's the perfect question. It comes down to the total amount of reduction you actually need to meet the regulations and also capital risk. Those cheaper, maybe lower efficiency systems, they're often easier and less risky to retrofit onto an existing plant. They're suitable for smaller facilities or maybe situations where you only need, say, a 60% cut to comply.
Ah, I see. So if the law only requires a moderate reduction, you might pick the lower capital cost option even if the per ton cost is similar.
Exactly. But if you're near a sensitive area, maybe a national park, and you need 95% or even higher removal, then you really have no choice. You have to bite the bullet and pay the high upfront cost for the high-efficiency wet scrubber. The
Sure.
total pounds or tons of pollution removed dictates the choice, driven by the regulations.
Okay, that totally reframes how you'd approach that decision. Let's shift gears now to the second big air challenge. Oxides of nitrogen, NOx. That's NOx, usually a mix of NO and NO2. Unlike SO2, which is mostly in the fuel, NOx is process-derived, right? Created by the combustion itself.
Precisely. It's formed during the burning process, not just carrying with the fuel, although fuel nitrogen does contribute. This means controlling it requires messing with the flame itself. We usually break down NOx formation into three pathways. The big one, especially in high-temperature boilers, is thermal NOx.
Thermal, meaning heat-related.
Exactly. It's super dependent on temperature.
Mm-hmm.
When you get really high flame temperatures, the nitrogen N2 and oxygen O2 that are just naturally present in the combustion air react with each other. The hotter it gets, the more thermal NOx you make. It increases exponentially.
Wait, what's the second pathway?
That's fuel NOx. This comes from nitrogen compounds that are chemically bound within the fuel itself. Coal is a big source of this. In many uncontrolled coal flames, this is actually the dominant source of NOx.
Got it. And the third?
The third is called prompt NOx. It forms very quickly, right near the flame front, involving hydrocarbon radicals. In large utility boilers, it's usually a pretty small slice of the total NOx pie compared to thermal and fuel NOx.
So for control, the key takeaway seems to be manage the temperature and manage the oxygen. Hit those two, and you reduce the two biggest NOx sources.
You nailed it. Lower the peak flame temperature, limit the oxygen available right where the fuel is burning fiercely, and you can significantly cut down NOx formation.
Which brings us back nicely to process modification, and those low NOx burners, LNBs you mentioned earlier, they're the go-to prevention method.
Absolutely. LNBs are really clever bits of fluid dynamics and combustion engineering. They work by carefully controlling how the fuel and air mix. It's called stage combustion. By slowing down that mixing, they create a bigger, less intense flame, which lowers the peak temperature. That directly tackles the thermal NOx formation.
And the fuel NOx.
They address that too. Critically, LNBs create zones within the flame where there's less oxygen available right when the volatile parts of the fuel are first burning off. Less oxygen there means less fuel NOx gets formed. It's a really elegant preventative solution to stop it before it starts.
Very neat. But what if prevention with LNBs isn't enough? Or maybe you're trying to upgrade an older power plant that wasn't built with them.
Right. Then you have to look at post-combustion controls. These are methods that destroy the NOx after it's already formed in the flue gas, usually by reacting it with something.
Using chemical reagents.
Exactly. The two main technologies here are selective non-catalytic reduction, SNCR, and selective catalytic reduction, SCR. SNCR involves injecting ammonia, that's NH3 or sometimes urea, directly into the hot flue gas. There's a specific temperature window it needs, quite high, typically 870 to 1150 degrees Celsius, for the reaction to work well.
And how effective is SNCR?
It's decent. You can get maybe up to 75% NOx removal. The big advantage is lower initial capital costs compared to SCR.
But the downside is?
High operating cost. You're constantly buying and injecting ammonia or urea. Those reagent costs add up significantly over the life of the plant.
Okay, so that's SNCR. What about SCR, selective catalytic reduction?
SCR is the high-performance option. It can often achieve over 90% NOx reduction, sometimes even higher. It uses the same basic chemistry, reacting NOx with ammonia, but it employs a catalyst usually based on titanium or vanadium oxides.
And the catalyst lets it work at lower temperatures.
Exactly. Because of the catalyst, the reaction happens efficiently at much more manageable temperatures, typically around 315 to 370 degrees Celsius.
Sounds great, but I'm guessing there's a cost catch again.
Oh yeah, the catalyst itself is the major investment hurdle. It's expensive stuff. Initial costs can be up to, $14,100 per cubic meter of catalyst. And the catalyst degrades over time, so you have periodic replacement costs too.
Yeah.
It's a significant capital outlay.
So a clear trade-off. SNCR is cheaper upfront but costs more to run. SCR costs a lot initially but gets higher removal and might be cheaper long-term depending on reagent prices and removal needs.
That's a good summary. The choice depends on the specific plant, the regulations it has to meet, and the overall economics.
Okay, fascinating stuff on air pollution control. Let's pivot now, smoothly hopefully, over to the liquid world water pollution control. This field has also changed dramatically, hasn't it? Moving beyond just making rivers look less gross.
Yeah, absolutely. It shifted focus towards really managing public health risks and ecological impacts, again, driven by regulations like the Clean Water Act and RCRA for hazardous waste. And when we talk wastewater treatment, it's important to distinguish between municipal, sewage from homes and businesses, and industrial wastewater. Their goals can be quite different.
How so? What's the main goal for municipal treatment?
For municipal plants, the primary job is reducing BOD, that's biochemical oxygen demand, basically the food for bacteria in suspended solids. The legal minimum requirement in the U.S. is typically an 85% reduction in both BOD and SS coming into the plant. Or sometimes it's stated as an effluent limit, like getting the treated water down to 30 milligrams per liter or less for both.
And how do they achieve that? Mostly biological processes?
Yes, heavily reliant on biology. The workhorse is the activated sludge process, or maybe trickling filters. You're essentially harnessing natural microorganisms, giving them lots of oxygen and letting them eat the organic pollutants in the wastewater.
Sounds natural enough, but there's a byproduct, isn't there? Sludge.
Sludge. Yes.
Yeah.
The bane of many a wastewater engineer's existence. Well, the volume of sludge produced is relatively small compared to the huge volume of water treated. Managing it is incredibly complex and expensive.
What makes it so difficult?
Well, first, it's mostly water, so you have to thicken it, then mechanically dewater it using centrifuges or belt presses to get the solids concentration up, maybe to around 30% solids. But then you have to stabilize it. This usually involves digestion, either anaerobic without oxygen or aerobic with oxygen.
Why stabilize it? What does that do?
Stabilization reduces pathogens, odors, and the tendency to decompose further. Remember, this sludge can contain disease-causing organisms and sometimes accumulated heavy metals or other nasties. You have to process it to meet strict regulations before it can be safely disposed of in a landfill, or, ideally, beneficially reused as biosolids, basically a regulated fertilizer for agriculture. It's a whole process chain focused on volume reduction and making it safe.
A constant battle, it sounds like.
Okay, let's move beyond municipal treatment to the really tough stuff. Advanced industrial wastewater and hazardous waste streams. Here, the pollutants aren't just simple organics. They can be complex chemicals or toxic metals.
Right. For these, you often need more specialized, sometimes physical or chemical, separation methods. Standard biological treatment might not cut it.
What are some key technologies here? Well, one widely used technique, especially for removing dissolved organic compounds, is activated carbon adsorption, usually using granular activated carbon, or GAC. The principle is pretty simple. Activated carbon is incredibly porous. It has a massive internal surface area, sometimes hundreds or thousands of square meters per gram. Contaminants essentially stick to this huge surface area through physical adsorption. It's great for polishing water, removing trace organics that cause taste, odor, or toxicity.
Okay, the sources mention an equation for this, the Freundlich isotherm. 1Q is K1C. Can you break that down conceptually? What does Q equals K sub 1 times C to the power of 1 divided by N tell an engineer?
Sure. So dollars there represents the mass of the contaminant adsorbed onto the carbon, per unit mass of carbon. Think of it as the carbon's capacity. $2 is the concentration of the contaminant remaining in the water. K1 and dollars are constants that depend on the specific carbon and contaminant. Conceptually, what that equation usually shows is diminishing returns. As the concentration of the water gets lower and lower, the amount collars of carbon can still pick up decreases significantly. It gets harder and harder and takes more and more carbon to remove those last traces of the pollutant.
So you hit a point where it's just not efficient to keep loading that same carbon bed.
Exactly, which is why engineers often use multiple JA columns in series. You load up the first column until the contaminant starts to break through the end. Then you take that first column offline for regeneration or replacement, move the second column into the lead position, and add a fresh column at the end.
Maximizing the use of the carbon before breakthrough. Makes sense.
You squeeze every bit of capacity out of that expensive carbon. Another really important technique, especially for metals, is ion exchange.
Ion exchange. like in a home water softener.
Similar principle, but often more sophisticated for industrial use. It's great for recovering valuable metals from waste streams or removing toxic ionic contaminants like heavy metals, cadmium, lead, chromium, etc.
How does the basic chemistry work there?
It relies on special resin beads that have charged functional groups. For removing positive metal ions, conjugations, you'd use a cation exchange resin. A common form might start with hydrogen ions attached, let's call the resin ordol or text H now. When the wastewater containing a metal ion, say text M plus dollar, flows through, the resin grabs the metal ion and releases a hydrogen ion. The reaction is basically text plus cus plus text plus text plus cus text plus dollar.
Okay, so R sub 1H plus M plus tends to R sub 1M plus H pluses. The resin swaps the hydrogen for the metal.
Precisely. The metal stays on the resin and the water leaves cleaner.
But eventually the resin gets full of metal ions, right?
It does. That's the exchange capacity. Once it's exhausted, you have to regenerate it. You typically do this by washing the resin with a strong acid solution. The high concentration of hydrogen ions in the acid forces the reaction to go backward, kicking the metal ions off the resin and putting the hydrogen ions back on. So you get your $R resin back, ready for another cycle, and you end up with a concentrated stream of the recovered metal.
A very selective way to pull out specific ions. Neat. Okay, one more key area.
Yeah.
Membrane technologies. Reverse osmosis, RO, seems like a big one.
RO is incredibly powerful. It uses a semi-permeable membrane that allows water molecules to pass through but rejects almost everything else dissolved. Salts, organics, even tiny inorganic ions. It's used for desalination, creating ultra-pure water, and concentrating waste streams.
How does it work against normal osmosis?
Well, normal osmosis wants water to flow from a dilute solution to a concentrated one to equalize things. Reverse osmosis forces the water the other way, from the concentrated side, like salty water, to the dilute side, pure water, by applying pressure. And the pressure needed has to be higher than the natural osmotic pressure of that concentrated stream you're creating.
Yeah.
We're talking significant pressures requiring powerful pumps and robust membrane housings.
Sounds energy intensive. What are the big operational headaches with RO?
Two main enemies, fouling and scaling. Fouling is the general term for stuff physically clogging the membrane surface, suspended solids, biological growth, organic molecules sticking to it.
And scaling.
Scaling is more specific. It's when dissolved minerals in the feed water become too concentrated as water passes through the membrane, and they precipitate out as hard scale directly on the membrane surface. Calcium carbonate, KCO3, is a very common culprit.
How do engineers fight that?
Fouling requires careful pre-treatment of the feed water and periodic cleaning of the membranes. For scaling, especially with calcium carbonate, engineers often add a small amount of acid to the feed water to lower the pH. This helps keep the carbonate dissolved instead of precipitating. But yeah, RO systems are high performance, but demand careful operation and maintenance.
Okay, so pulling this all together, looking across both air and water, it seems like we keep seeing two main engineering philosophies at play.
I think that's fair.
On one hand, you have prevention changing the process itself to avoid making the pollutant in the first place, like the staged mixing in low-NOx burners.
Right. Process modification.
And on the other hand, you have a high-efficiency separation or destruction after the pollutant is already formed, like the SO2 scrubbers or the GAC and RO we just discussed for water.
Yeah, the end-of-pipe treatment. And increasingly, the overarching goal, the philosophy that regulators and companies are pushing for, is pollution prevention, P2.
Why the big push for P2?
Because at the end of the day, it's almost always more sustainable and often more cost-effective in the long run to not generate the waste in the first place. If you can modify your process to avoid making SO2 or hazardous sludge, you save all the capital cost of building the scrubber or the sludge dryer, and all the operating costs for reagents and energy and disposal. Prevention beats cure.
That makes a lot of sense. Which leads us perfectly into our final thought, kind of looking ahead. How do we optimize these incredibly complex control systems, running a power plant or a chemical facility to meet tight emission limits while still being efficient? It's tricky.
It's incredibly tricky. These processes are dynamic. Inputs like fuel quality can change, and the relationships, like NOx formation versus temperature, are highly nonlinear. Simple controls aren't always enough.
And our sources suggest this is where computer control, even artificial intelligence, is starting to play a bigger role.
Definitely. We're moving beyond basic feedback loops. Think about optimizing combustion in a large boiler. You're juggling fuel flow, multiple air injection points, temperature sensors, NOx analyzers, CO monitors. It's a complex dance.
So how could AI help an engineer manage that dance? What about methods like fuzzy logic or artificial neural networks?
Okay, fuzzy logic is interesting. It allows you to program control systems using more human-like fuzzy rules based on expert knowledge. Instead of saying, if temperature is exactly 900 C, do X, you can say things like, if NOx is high and temperature is climbing, then increase the overfire air slightly.
So it handles ambiguity better, like how a human operator might think.
Exactly. It lets the automated system make nuanced adjustments based on qualitative states, not just precise numbers, which is often how real-world systems behave.
And artificial neural networks, ANs.
ANNs are more about pattern recognition and learning from data.
Mm.
You could feed an ANN vast amounts of historical operating data, all the sensor readings, the control settings, the resulting emissions. The network learns the complex, often non-intuitive relationships between all those variables. Then, in real time, it can analyze the current state of the plant and predict which combination of control settings will keep production efficient while simultaneously minimizing pollutant emissions, keeping you within your permit limits.
So it's like finding the operational sweet spot automatically, constantly adjusting based on learned patterns.
That's the goal. An automated system that continuously optimizes that complex trade-off between production efficiency, cost, and environmental compliance. It's about turning that engineering challenge into a real-time automated solution.
A fascinating glimpse into the future of process control and environmental engineering. Until the next equation design junkies, we're mechanical engineering made simple.